Does it work? Yeah. So thanks for the kind introduction. And yeah, as already mentioned, this talk does not consist any or contain any AI, any deep learning, any neural network. Sorry for that. Yeah, but I hope it's still interesting for you. You'll see about that in a second. I'll quickly like to begin with a short introduction of our working group, what we do at KIT in Germany, and we are doing DAQ systems for all kinds of physics application. So on the one hand, some of my colleagues are part of high energy physics. So they are part of the Serenity Consortium here at CERN, building the Serenity board, which is mostly used within the CMS project. And on the other hand, we have these two applications, so the frequency multiplex readout for quantum sensors and the control platforms for qubits and qubit characterization, where these two applications are quite closely together and we can share a lot of the code base and the hardware. My main focus is here, this part, which is also the topic of the talk today. And I'd like to introduce two experiments that I currently work on. The first one is ECHO, where we try to find the upper limit of the neutrino mass by using so-called magnetic microcalorimeters. So these kind of sensors are working at superconducting temperatures at below 1 Kelvin. So we put them into a cryostat, and since you don't want to put too many cables into the cryostat, which would increase the heat and then reduce the temperature sensitivity, we use some frequency multiplexing approach. So we have here one array containing up to 400 pixels. And each of these pixels is connected to its own resonator frequency. So what we do from room temperature, we generate a frequency comp containing exactly these frequencies. And then once one of the pixels gets an event, it will amplitude modulate just this single frequency. And this comp is then sent back to the room temperature and can be further processed by the DAQ system. These MMCs are specialized because they have a very high bandwidth of up to 1 megahertz. So they offer a really high time resolution, and also the biggest advantage of these superconducting sensors is the immensely good energy resolution. So this is why they are used for this experiment. The second one is quite similar in its structure. It's BULLKID. It's a quite new experiment we just started last year. Where we want to detect dark matter by using some different kinds of sensor which also operate at the superconducting temperatures. So these ones are called kinetic inductance detectors. They operate similarly, so they also are coupled to a specific readout resonance frequency, and we need this frequency comp to stimulate them. The difference is that they have much lower bandwidths. So the signal rise time and the time resolution is much smaller, but that means that the resonators on the frequency band can be placed much more densely. So you can add more detectors in one line. And as mentioned, we at KIT we built the room temperature readout electronics for these systems. So here there are the two examples. This is the prototype for the BULLKID experiment, and this one for the ECHO board, or the ECHO project. We decided to use the AMD Sync UltraScale Plus device family and support both MP socks and RF socks. So for the ECHO experiment, we have this MP sock with an external board containing the ADCs and DAQs. And for the new BULLKID project, we use this RF sock that has been mentioned in the morning already, containing the converters directly. The firmware of the PL is written in VHDL. Currently, we operate with Vivado 2020.2. And then this whole device image containing the Linux for the MP-SOC is built with a custom build system based on Yocto. So coming back to one of the problems or one of the challenges that we have, this is an example of the frequency comp that we need to generate. And this is actually the example of the BULLKID experiment. So this one is containing currently, I think, 64 tones at these specific resonator frequencies. We need to generate this comp at real time, and then also, more importantly, do the analysis. The problem is that the tones are non-uniformly spaced due to the manufacturing processes of these resonators, and we need to find a way to somehow process them independently. The intuitive solution for that would be to just use digital downconversion. So by taking this pure readout tone, mixing it to this amplitude modulated one, low pass filtering it, and then you get the amplitude modulation back. So this would be a quite easy approach. And also there we would be really flexible because you could select for the down mixing every frequency you like, and the time resolution would be optimal because you operate at the sampling rate of the input. However, this approach is not really scalable because for each single tone you would need this generation module, this complex mixer, and this low pass filter. So yeah, once you need to downconvert 400 sensors, which we need to do in our application, the DPL resources are just exceeded by a lot. So there's a different way how to do this, which I want to introduce now, which is the so-called polyphase channelizer. And just a disclaimer, so these two slides are probably the most difficult one to digest. I try to be really high level, so if you're interested in the details, you can take a look at this paper. It's not from me, I just stole all the diagrams from there and copied them, because I think they explained it quite nice. Yeah, but this algorithm is basically based on an FIR filter that has been broken apart into different sections. So imagine we have an input spectrum here containing 4 sections of interest, here displayed by these different shapes. So we would break this FIR filter up into 4 different parts and delaying each of these parts by 1 clock cycle and then doing the data rate decimation. And this structure would then end up in an intermediate output like this, where we have these 4 subbands that are shifted in phase. So the first one, since there is no delay, would have all of the 4 subbands on the real axis, and then the second one, there's the green one is shifted 90 degrees to the imaginary axis. And due to this down conversion here, these are subsequently at the output coming on a common readout line. So then you see here these 4 intermediate results again, and now by using some rotation metrics, we can reconstruct the pure subbands again. I don't think I have time to go through all of this, but you can check the slides and do it yourselves. But how it works, if we just sum these up, we would end up with the pure signal of the blue triangle, while all the other 3 subbands are eliminated because they are just rotated by different angles. And then you end up with this. And the really nice thing about this algorithm is that this rotation matrix is exactly the discrete Fourier transform operation, which is really nice. Above all, if we try to stick to 2 to the power of n channels, because then we can replace this with an FFT, basically. And this is what the whole algorithm is about. And this is what we put our channelization concept on. So what we did, here you see the example parameters for the BULLKID experiment. We have this wideband input spectrum and divide this by the channelizer into 64 equidistant subbands. And then in each of these subbands, our resonator tone of interest could be anywhere because they're non-uniformly placed. So in the second step, we have, okay, actually this is wrong. I need to fix this. So it's not a bandpass filter. This is now a DDC. So we just select the frequency wherever this tone is and mix this one down with a 200 kilohertz low-pass filter. And this allows us to get the data from wherever in the spectrum it is. You see one problem. In the middle of these subbands, there are some blind intervals. And we need those blind intervals as well because our tones could be anywhere. So what we did additionally, we copied the input spectrum, shifted it a little bit to higher frequencies, and performed the same algorithm again. And due to this shift, now these subbands are exactly in the blind intervals of the original spectrum. And with this, we have the full spectrum covered and can reconstruct every tone. How does this look like now in the block diagram form? So we have this 3-stage concept where the first one is just this mixing of the input spectrum. Then we have for the original and for the shifted one this polyphase filter bank, which I just explained. And then in the first stage, for both of them individually, this fine downconversion to bring the resonator tones to DC. Yeah, let's look at these three stages a little bit more detail. So I guess most of you know how an NCO works. It's just some numerically controlled oscillator, where we know at build time that the frequency needs to be set to half of the spacing of the subbands, because then we have exactly this middle of the blind intervals. And since we know this at build time, we can dimension the memory for the NCO so that the read pointer is exactly incremented by 1. So we just need the amount of samples that we really need, and there's no waste. For this complex mixing, we make use of the DSP slice available on the Sync UltraScale Plus. So this is also quite efficient solution. The second one, I'll quickly go about this. There's also some more nice feature, because both the FIR compiler and the FFT exist as IP cores from AMD. So we don't need to take care about them at all. They offer all the features that we need. So the FIR compiler, they have multiple channels. And we just need to define the coefficient files, for which we created MATLAB and Python scripts. And then it even has an option to have parallel paths, which we made use of. So we have both the original and the shifted spectrum through the same FIR filter, because we want to use the same coefficients. So there's just one FIR filter instantiated, and then we split up the output and use an FFT for both of them. And due to some mode of operation of the FIR compiler, the channel order needs to be reordered. This would go into too much detail, but you can see this Xilinx application note here where this is explained. So we have here our custom block which reorders the samples at the output. The third one, this fine downconversion. Now basically this is the same task that we had originally, with the difference that now we have multiple tones in TDM scheme. So we can use one NCO to create the mixing frequencies for multiple channels in an interleaved pipeline. So this is done by just jumping around across these memory and selecting and creating the frequencies here for the individual channels. And then you get only the amplitude modulation at the output. So let's quickly look at the resources. So there are a lot of numbers that you don't need to remember. So the first one, the spectrum shift, we can neglect immediately. What I just want to draw attention to is that even if the polyphase filter bank requires a lot of DSPs, remember that for the brute force approach that I explained in the beginning, we would need these 3 modules for each channel. And then you can do the maths yourselves. If you multiply this by some channels, you would quickly increase the amount of DSP slices for the polyphase filter bank. So I guess this is quite, we see that our implementation is quite successful. To prove that this really works, this is the output. I swept one tone across the whole band of interest and looked at the output of the individual channels. And since you see for each frequencies, there's just one single channel that has an active output. And since this only takes into account the original spectrum and not the shifted one, you also see these blind intervals in between, where the second one would then come in. The last thing I want to mention is just the sensitivity of this whole thing. I did this by measuring the power spectral density and compared one loopback just of our electronics and one measurement where the whole cryogenic infrastructure, including the multiplexer and the sensors, were included. And what you see here, that the blue curve, so this RF loopback, is always lower than the cryogenic setup, which means that our system is not the limiting factor for the readout sensitivity, which was one of the requirements of the physicists. So this is already the conclusion. I'm done. We implemented a full channelization stage for multiple parallel tone processing, which is capable for our application of quantum sensor readout. And this system is modular, so you can select the input frequencies, the number of channels, the bandwidth, whatever, for whatever the requirements of the experiments are. So it's easy to adapt this in case we have a new experiment. It's very efficient, and we can further process the tones in time division multiplex, but for sure there are some drawbacks, which is here mostly the limited separation capabilities. since due to our architecture of this third stage, this fine downconversion, we can only have one tone per subband that can be mixed to DC. And also we're limited to 2 to the power of n subbands, otherwise we would lose the effect of the FFT implementation. So if you ever have the same problem and need to frequency demultiplex tones, maybe this is a solution that could also work for you. Thanks for listening.
Questions?
Thanks for the great talk. So there are companies who are now implementing FIR filter as a RISC-V extension. You know, they are for this audio and all. You know, there's ANC and all that also uses FIR filter. I don't know if with that, if you ever go with that kind of solution, does it kill the flexibility or is the scale or what power? But they are people who either use a DSP, let's say, with a SOC, or use these kinds of extensions and then tape out and all. So have you considered that or rejected that due to any reason?
So we didn't consider that. I just looked if there's an IP core available, and since there was one directly from Xilinx and it offered all the features that I need for this application, I just did it. So I didn't look at any other options because this FIR filter that we used works perfectly fine. Yeah.
More questions? So I actually have a question. If I understand you correctly, you have 2 different experiments you said in the very beginning. And then I remember the detector bandwidth is quite different.
Yeah.
Is this a solution for both of them?
It's a solution for both of them because by selecting these coefficient tabs in the FIR filter, you can select how wide the subband should be.
Okay.
So yeah, you can just adapt this to your own application that you need.
Great.
Which is quite nice. Yeah.
I know. Excellent. Thank you. More questions for Timo? If not, let's thank him again. Thank you, Timo.